Okay, so one of the major problems with GaN, fantastic technology, it's the next generation technology for power transistors, but what is the main problem that people are having with them? So the first main problem that we're talking about is EMC, basically the radio frequency interference that you get when you switch the transistors. We all know silicon, IGBTs, FETs, that's where we've come from, and they switch in 20 to 100 nanoseconds. And over the years, power engineers have worked out how to actually use these, how to construct them, you know, how to get around, mitigate the EMC problems. And there are sort of techniques that engineers use, and that is now mature. That can be done. So SiC has come along. It has all sorts of advantages. It's got better thermal characteristics, better resistance, IDS-on is lower, and various other things. But one of the side effects of the technology is it switches faster, so it's now sort of 10 to 50 nanoseconds. So the power spectral density of these signals when you're switching at much faster rates, edge rates, is much higher. So you've got higher frequency components, and all of a sudden these technologies, these techniques that power engineers have built up, they don't work anymore. You can't use the open construction anymore. So what do we have to do? So for SiC, to make it work, you have to sort of arbitrarily sort of reduce its switching frequency to about 100 kilohertz. And you also have to reduce the switching transition times, probably closer to the 50 nanoseconds, in order to pass EMC with the same construction techniques that people have used for silicon in the past. Now GaN comes along. GaN is an awesome technology, but it's super fast. And that's a great thing, because by switching really, really fast, the area under the graph, under this sort of VI graph here, is very much smaller, so you're dissipating much less power. But the problem with that is, with 2 nanosecond transitions, you've got 500 megahertz plus frequency components. And with an open power supply construction, which is typically what people have been using for decades, that just doesn't work anymore. So in order to use GaN, people are doing various things. For instance, there's controlled speed GaN coming out, where you've got the driver and the GaN transistor integrated on a die, and essentially controlling of the speed of the gate, so that you can change the speed of transition from on to off. Now that's great for EMC, because it reduces your power spectral density, but it means you're now dissipating power for a much longer time. So the energy under the graph, the power that you're dissipating, is greater, so you lose efficiency. So that's not a great solution. So yes, you're using GaN, but you're not really getting the best out of it, because you're actually slowing it down. And even with the controlled speed of switching in these integrated solutions, they're still slower than our technology, which switches in a couple of nanoseconds. So they're still using much more power than they need to. And in reality, in order to get them to pass EMC, you have to come back to this kind of speed. So you're losing all of the advantages of GaN. So the switching, the high-speed switching, is a wonderful thing for potential efficiency, but it gives a really big problem that you can't use it in practical systems without slowing it down, and then you lose the efficiency. So our solution gets around all of this with various proprietary technologies. So we switch as fast as humanly possible. So we get the best possible efficiency. And of course, there's lots of RF as a result of that. But we have another technology called whisper GaN, which is a construction technique and a packaging technique which allows us to switch at those frequencies, but without having EMC problems. So that's a proprietary technology that will soon be patented. But that allows engineers to essentially use this kind of technology, the old-fashioned sort of packaging, mature technology that they've used for decades, but to get the ultimate efficiency of GaN, switching at its highest possible speed and the lowest possible power dissipation. And that's the real USP of our technology in terms of the switching speed.